We're working in section 2.3. We've been talking about functions and relations and domain and range. We've talked about whether a graph or an equation could represent a function. We've also talked about whether a table represents a function. And now we want to go on to these last two topics. We want to talk about function notation, and we also want to talk about increasing and decreasing functions. So let's start with a quick example here. Here's a problem you would have seen in a previous math course. It says if y equals 1 minus x, then find y when x equals 0. And so then the solution is just to replace the x with 0, and you would have y equals 1 minus 0, or y is equal to 1. And if you think of this as a function, right, y equals 1 minus x, then you have an input 0 that makes an output 1. And so you could even think of the ordered pair 0, 1 on the graph of this function. So what we want to do now is we want to introduce the idea of function notation, and all that means is that we're going to replace the y in our problem with f of x. So now, instead of saying y equals 1 minus x, we say f of x equals 1 minus x. And f of x means the same thing as y. So in particular, the f is a common choice of letter here. Sometimes we use other letters like G or H or something else, but f is the most common. F for function. And then x here tells us exactly what the independent variable is, the input variable. And so we sort of took it for granted before that x was the input, but there's some good reasons to state it explicitly. And so that's what we've done. F of x is equal to 1 minus x. And so if we just look at this first example here, f of 0 says replace the x with 0 in the function and see what the output is. So 1 minus 0, which is just 1. So of course we get the same answer as before because it's the same problem. It's just a new notation. And again, it's worth pointing out that there's an ordered pair 0, 1. Okay, so let's do it again. Let's go on to this next problem. This time we're looking at the g function. G of x is x squared minus 3x minus 4. And so we're just going to replace the x here with negative 3. And so we need to put a negative 3 in for x. And we get negative 3 squared minus 3 times negative 3 minus 4. You have to be just a little bit careful with the algebra, right? The negative 3 gets squared to make a positive 9. If you didn't have those parentheses there, then you would be saying that you're only going to square the 3 and not the negative sign, and then you'd wind up with a negative 9. So that's a mistake that I see students make sometimes. So at any rate, the answer is 14, and we can see that the g function has an ordered pair, has a point, negative 3, 14. Okay, one of the nice things about function notation is that it gives us a convenient way to indicate lots of different inputs besides just a number. So in this case we have g of negative x, And so that just means that we're going to replace the x with negative x. So instead of x squared, we have negative x squared minus 3 times negative x minus 4. And then, of course, we're squaring the negative to make a positive, and we're squaring the x to make x squared. And then there's a plus 3x minus 4. So here's our answer. One of the nice things about function notation is that when we look at this answer, we can see exactly what the input was that made this output. So input and output go together, and so it's nice to see them side by side here. Oh, one more thing. Replacing x with negative x is an important idea later in this chapter. So we'll see this again real soon. Okay, one more problem here. This time we have f of x plus 4. So f of x is 1 minus the input. 1 minus the input. This time the input is x plus 4. And so be careful when you distribute, and make sure you distribute to each term in the inside the parentheses, and our final answer will be negative x minus 3. Okay, so that's the basic idea of function notation. Here's a similar problem, not quite the same. For example 6. It's nice because there are a couple of ideas there that we'll see in the next section. So in particular, this is the equation of a line, and we're going to be studying lines in section 2.4 and 2.5. So all we need to do is just follow the directions here in part A, solve for y in terms of x. So if we have x minus 4y equals 8, then we could subtract x on both sides. We're trying to isolate the y, so we want to isolate the y term first. We want to subtract x off, and we'll have minus 4y equals minus x plus 8. You could write x. You could write 8 minus x instead, although if you remember studying the equation of a line before, you might remember that it's nice to put the x first and then the constant at the end. Okay, and we need to divide both sides by negative 4, and so we get y equals, and then negative x divided by negative 4 would get you positive x over 4, and then 8 divided by negative 4 would get you a negative 2. And that's a good way to write the answer. It might be even nicer if we wrote it as 1/4 times x minus 2. Then if you remember, the equation of a line can be written in the form y equals mx plus b. Then we can see that the m, the slope, is 1/4. And if that doesn't sound familiar to you right now, don't worry, we'll be going over it in the next section. Okay, so here is our answer for part A. And then in part B, just replace f of x with, replace y with f of x. So we can write f of x is equal to 1/4 times x minus 2. And then in part C, we can find f of 3. So x gets replaced by 3, and we have 1/4 times 3 minus 2, which is, what is that? 3/4 minus 8/4 would be negative 5/4. And we're all done. Okay, so that should take care of function notation for now. The last thing that I want to talk about here in the section is increasing, decreasing, and constant functions. Let's get an informal definition. An increasing function is one that's rising from left to right. And so I could give you a little example here. Nothing fancy. from left to right, we're going up. From left to right, we're going up. And then a decreasing function would be going down or falling from left to right. And a constant function is horizontal. It's neither increasing nor decreasing. There are formal definitions for increasing and decreasing that we'll see in calculus, and those definitions become real important late in that course. But for now, just this informal understanding will be sufficient. So let's go ahead and look at this last example here. Let's just determine the intervals where the function is increasing, decreasing, or constant. And so we're going to work from left to right. And so let's see here. On this first section, maybe it's good to cut the graph up. Here is x equal 1. And to the left of 1, can you see that the graph is increasing? Remember, we go from left to right. We're not going to follow this arrow down to the left, right? We're going to come from the left and we're going to go to the right. And as we do that, we see that the y values are going up or increasing. And so we say that the graph is increasing on the interval here. Where does this interval begin? Well, this arrow back to the left says that we're going from negative infinity up to 1. And notice when we talk about an interval for increasing or decreasing, we're talking about an interval of x. We're not saying anything about what the y values are, except that the y values are getting larger or increasing. So so these are values for x. From negative infinity to 1 is an interval of x. From 1 over to x equals 4, we can see that the graph is constant. And then after that, beyond 4, the graph is decreasing. So from 4 to infinity, decreasing. One more thing I want to say about this answer. Notice we're using parentheses, not brackets. Even though there is a point here at 1, 3, we don't want to use a bracket to include that point. And so that is a convention that goes back to the formal definition of increasing and decreasing, which says that we always do it on an open interval. And so that's the definition in our textbook. And it actually gets a little bit confusing because there are other textbooks that will define increasing and decreasing on a closed interval, but not our textbook. So let's not worry about that. You can see why you might not want to use a bracket here. If you had a bracket on the at the 1, you'd have a bracket for this increasing interval and also for this constant interval, and then it sounds like you're increasing and constant at the same time at the edge of the interval, which seems a little counterintuitive. So that's one reason that it might seem like a good idea to always use parentheses. So again, always use parentheses for intervals increasing, decreasing, and constant. Okay, last one. Maybe pause the video and try it for yourself. We start out from left to right, decreasing, coming down to the point at negative 3, 3. So we're decreasing from negative infinity to negative 3. And then we're constant from negative 3 to positive 3. Again, those are values of x. And then we're increasing on the interval from 3 to infinity from left to right. Now we're going up again. The fact that there's a discontinuity, a jump here from the point at 3,3 to 3,1 doesn't matter for us. What matters is that to the left of 3, the function was constant, and to the right of 3, the function is now increasing. Okay, that's all for section 2.3.